All right, everyone, let's do section 2.5. 2.5 and 2.6 both are going to be a lot of applications of integrations. So some word problems, a lot of physics, but some introductory physics. Okay, so we'll start off with a mass. We'll start off with a one-dimensional object and then we'll move up. So it's kind of a weird way to say this, but a one-dimensional object technically doesn't really exist in the world that we live in because it always has some dimension to it. But imagine a really thin pen or a really thin piece of wire, maybe that might a really, really thin rod or wire. For mathematical purposes today, we're going to assume it's thin enough to be treated as a one-dimensional object instead of a three-dimensional object that it actually is. So we're just kind of making a little bit of an assumption here. So we're going to start off with that. We're going to try to think about finding the mass of that object. So think of it like an actual pen maybe that you're holding in your hand. You could probably imagine that the pen might be a little heavier on one side than it is on the other, depending upon maybe where the ink is lying or what material it might be made out of. And so perhaps the density on one side versus the other is a little bit different. So we're going to think about that density. If the rod has a constant density, let's say if it's the same everywhere, and we're going to use the variable rho. This means rho. I should write that down for everybody here. You should write that down as well. Rho is just the Greek letter, and it kind of looks like a letter P, I know, but that's just the Greek letter that we tend to use for density. So if the rod has a constant density of rho, given in terms of mass per unit length, then the mass of the rod is just the product of the density and the length of the rod. So mass would be B minus A times rho, or let me highlight what the B and A are. So B minus A would just be the distance or the length of that thin rod or wire. But then, of course, what if the density is different? So if the density of the rod is not constant, then we can use the linear density function rho of x. So that just means rho of x is now a function of x, which means maybe it depends upon where I am on that object, and the density might be changing. That's all that's saying there. Okay, so if that's the case, then to denote the density of the rod, rho of x is to denote the density of the rod. Then to find the mass of the rod, we're just going to integrate the density function. So you're adding up every small little piece. You're finding a little bit of mass right here, and then a little bit of mass right there, and then a little bit of mass right there. But you're kind of doing it as small little slivers along the way, which adding up, technically we should do infinitely many, and then remember infinitely many, thinking of Riemann sums one more time, was really just the integral. So all that to say is the mass is the integral of the density function. And if you're taking notes, which I hope you are, I recommend that instead of just memorizing this formula, that's not as good, I would think of this as mass is equal to the integral of the density function. The integral of the density function is a better way to keep it in your mind, okay? All right, so it's the integral of the density. So let's do a quick example so we can get used to some of this stuff. So consider a thin rod on an x-axis, let's just say over the interval from pi over 2 to pi. I'll draw a picture of that. I always recommend that you draw a picture. You might reach a point where you can get away without drawing a picture, which is totally fine. It really genuinely is completely fine. You certainly don't need to, but I still recommend it until you've mastered it. And so one thing I want to point out about that picture is it's actually only on the x-axis. So I don't even need the y-axis on my picture at all. It's just on the x-axis. I have this starting at the value of pi over 2 and ending at the value of pi. Here is my thin rod. Now I've made it maybe kind of thick here, but think of it like a thin little wire there is what you're thinking of that as. And then what I know is that the density of this rod is given by rho of x equals sine of x. So you're not going to graph the sine function. That's not what this is. Sine of x, the output of sine of x, is just describing the value of the density along this way. So if I were to think about, let's say, 3 pi over 4, which is somewhere right around here. If I plugged in 3 pi over 4 into the sine function, I get an output of some number. I don't even know what it is. It's like 0.7. It doesn't matter. Then that just means that at this moment, the density is 0.7. And maybe over here, the density is 0.9. And maybe over here, the density is 0.3 or whatever the numbers really are. So the sine function is just telling you the density along that rod. So you don't actually graph the sine function. That's just telling me the density. So then here we have it. We have mass is equal to the integral of my density function, which in this case was sine. So from pi over 2 to pi, then we integrate the antiderivative of sine is negative cosine, and I evaluate that from pi over 2 to pi. I'm going to show all the work. So negative cosine of pi minus negative cosine, negative cosine. There it is, of pi over 2. And then we can go from there. Negative cosine of pi is -1. Cosine of pi over 2 is 0. I had to think about that. Yeah, we definitely have to try to remember our unit circle. Those two negatives canceled, and I got 1. I don't have any units of measurement in this problem, so you don't have to give me any units of measurement unless I give you units of measurement. Ta-da! All right, that's how you find the mass of a one-dimensional object. Now, obviously, not everything is going to be a thin wire. What if we have now a two-dimensional object? Let's think of that like a plate. So that's what we're going to start off with next, the mass of a two-dimensional object. Extend the idea to find the mass of a two-dimensional disk. You might want to think of that word disk. Think of it like a plate, like an actual like dinner plate, like an actual round circular object that you have, like flat circular object that you have in front of you. If it's a disc or a plate, that means it has a radius. Let's just say that radius is r. Assume the density is given in terms of mass per unit area. That's called that area density. Then further assume that the density varies only along the disk's radius, called the radial density. Okay, that sentence is actually kind of confusing. So I kind of want to highlight that and talk about what that means. So it was assume the density varies only along the disk's radius. Let me zoom in and tell you what that means. This is going to be kind of important here. You really want to understand what's happening here. That means that if the density right there, let's just say is one, I don't know, gram per centimeter squared, something like that. It doesn't matter what the units are, 1, then that means it's 1 everywhere along that small little circle. And then let's say, for example, the density right here is, I don't know, 3. If the density right there is 3, then the density is 3 all the way along that circle. That means it was 3 everywhere. If the density, let's say right here, is 0.7, then it's 0.7 all the way along. So that's what we mean by a radial density, is that the density changes throughout the plate, but the density is the same on each little interior circle or piece of that disk. Okay, that's what we mean by the radial density. We can then orient the disk in the XY plane, which I've done. So really that means because of that symmetry, I can really only need to look at right here. That's kind of why it's sort of nice. If you have some symmetry, you only have to look at one spot. Because I don't need to go backwards. I already know that they're going to be the same radius along the same density along each of those radii. All right, so I can orient the disk in the XY plane with the center at the origin. The density of the disk can then be treated as a function of x. We're going to call that still rho of x, just like it was before. Then I can partition it into small little tiny washers. Maybe I should do infinitely many, hence the integral, ta-da. All right, that's where it's going to come down to. So here we have it. So here's my theorem. Rho of x is an integrable function representing the radial density of a disk. Then the mass is going to be equal to the integral from 0 to r. The 0 to r is just from the center to the edge of that circle of 2 pi x times the density. The 2 pi x, let's talk about where that comes from, okay? Let me talk about the area of each small little washer. Well, the area is always, well, let's think about the circumference. Let's take this little small sliver right here and flatten it out to a straight line. Wouldn't its length be the circumference? And don't we know the circumference is 2 pi times the radius? And then it has to be times the width of each of those washers. One more time, if I take that little washer and I just flatten it out, the length was the circumference, which is right here. And then the width is that delta x, right? The width, that's going to be the area of each one of those. And the circumference, or sorry, the radius was actually x because the radius kept changing on each one of those little pieces. So that's where we have this. I'm going to label some of that for you. This is what you want to write down. So 2 pi x was the 2 pi radius. That was the circumference, not of the whole disk, of each small little sliver. And this right here was the width of each washer, of each little small sliver. Okay. All right, and then you add up infinitely many, hence the integral. That's where that came from. Okay, all right. So we had to still multiply by the density. You always take that area and multiply it by the density. So the area of each washer was this guy right here, this one and this one. There we go. And then of course we have to think about that density. So you multiply it by the density function as well. Ooh, all right, let's go ahead and do an example. Kind of a lot. Let's go ahead and just do an example. It'll maybe make a little bit more sense. So now I have rho of x is equal to the square root of x is the radial density, there we go, sorry about that, of a disk. Calculate the mass of that disk of radius 4. So this is another one where I recommend you draw the picture, but you might not need to because it's a circle. So maybe you don't feel the need to draw that, and that's totally fine. But there it is. Here's my x-axis. I'm still going to draw that x-axis. That means that that's the origin. 0 is at the center. This disk had a radius of 4. That means it crosses the x-axis at 4. The reason why that's so useful, because then that tells you the bounds. You can see that from the picture, the 0 to 4 covers all of the radii of each one of these small circles. Okay, so that's that integral. And then I have my formula 2 pi times x times the density function dx. Then we can do the calculus. Okay, so 2 pi is a constant multiple, so I can take it on the outside, and then x times the square root of x is x times x to the 1/2. And hopefully you remember that you need to add those exponents in order to multiply them, so that becomes x to the power of 3/2. Then I can do the integration, so 2 pi, add 1 to the power, so 3/2 plus 1, divided by the new power, evaluated from 0 to 4. I'm going to simplify right away. I find it easier to simplify right away. This will become 4 pi over 5 times x to the 5/2 evaluated from 0 to 4. And then I'm going to run out of space, of course. So I'm going to go over here to simplify it from here. So then I have 4 pi over 5 times 4 to the power of 5/2 minus, when I plugged in 0, I got 0. So 4 pi over 5 times 2 to the power of 5. That's because the square root of 4 is 2. And then that becomes 4 pi over 5 times 32. And then I have my final answer of 128 pi fifths. Ta-da! That's our radial density there. Radial density, finding the mass of a two-dimensional disk. All right, so now we have ideas of mass, which is great compared to the density. Now we're going to talk a little bit more of a few other physics applications that use integrals, and that's going to be work, force, and springs. So here's a quick definition that we're going to start off with as a reminder. Maybe you know some of this from your physics courses or even from your Calc 1. If a variable force, f of x, moves an object in a positive direction along the x-axis, so you have an object that starts here and you move it over here, okay, all right, there's a force that does that. If it moves it from A to B, so starting from one point to the other, then the work done on that object is the integral of the force. So in general, work is often thought of as work equals force times distance. But that's if your force is constant. And so the possibility of force changing a little bit means I have to add up all different small pieces of that force that might be changing, which is why it became an integral. Okay, so that's kind of the way to think about that. All right, but let's go ahead and do an example so we have a general idea. Find the work done when a constant force of, let's just say 11 pounds. I know that's not a great unit of measurement. Sometimes your textbook uses that. We're going to use other newtons later on, but let's just go with it for now. I know it's kind of silly. Moves a chair from x equals 0.7 to x equals 1.5. So just to practice with the general idea, work, let me get a better color there. Okay. Work is equal to the integral of the force function. So my force was 11. Really easy, not always going to be that easy. This one just happens to be easy. And then you just integrate it. The antiderivative of 11 is 11x. You evaluate it from 0.7 to 1.5. So I have 11 times 1.5 minus 11 times 0.7. Use your calculator. I got 8.8. The units of measurement here is not great, I know, because we weren't using newtons and meters. Here we're using pounds and feet, so it's just foot-pound is the unit of measurement of work there. Ta-da! That's it. Okay, let's do it a little bit more. So find the work done now in lifting a 13-kilogram child from the floor to a height of 2 meters. Here, what's interesting is we're not really given a force. We have to think about it. So I did give a nice little hint here. Note that 1 kilogram equals 9.8 newtons. So we have to remember that. There's also another thing to think about that is not written, but I want to remind you, we know what acceleration is on planet Earth. We know that the acceleration on planet Earth is 9.8 meters per second squared. And we also know that force is equal to mass times acceleration. That's Newton's second law of motion. So that means that my force, in this case, the mass of this object was 13. The acceleration that is acting on this object is the 9.8 meters per second squared because you're lifting something up. Acceleration due to gravity is always pulling us down. And then you can type that into your calculator if you'd like, and I got 127.4, and that really is going to be in newtons there, but either way, there we have it. Cool, cool. All right, that's not so bad. Okay, so now I have my force. Let's go through and find the work. So then I can do what my work is, which is just going to be the integral from here to here, so from the beginning to end, so 0 to 2 of my force, which is 127.4. And then you can go through and do that calculation. I got 254.8, and that one really is in joules. Ta-da. Cool. All right, let's keep going. Let's keep going. All right, now we have this general idea of force. Let's think a little bit more about that force when it applies to a spring. So Hooke's law is the force required to compress or stretch a spring. So think of it like an actual spring, like a slinky or something that you have in front of you that you can stretch or compress. Hooke's law says that the force required is always going to be proportional to the distance away from the equilibrium, which is a fancy way of saying that the force is equal to K times X for some constant K, and that K is going to change depending upon the spring. Maybe the material the spring is made out of, maybe the length of the coils, how far apart the coils are, lots of things could come into play there. But that constant K is going to be constant for that particular spring. Every spring is going to have its own constant, but once it has a constant, that constant is going to be applied to X for the force function for that spring. That's Hooke's law. So here's an example. So the example here is a 1 meter spring requires 10 joules. Joules is in work, so maybe make that note to yourself. That means that's work right there. To stretch the spring from 1.1 meters in length. So that means that X is going to go from 0 to 0.1 for the spring to stretch from 1 to 1.1. It was already 1 meter long. So that's equilibrium. To go from 1 to 1.1, so equilibrium is 1 meter. So that means I haven't moved at all. So that's actually 0. Then I moved the 0.1 meters over. All right, so then that's something to keep in mind. How much work would it take to stretch the spring from 1 meter in length to 1.3 meters in length? Let's start off with that very first thing. 1 meters, I know the length of the spring. That's the initial. 10 joules, that's work. 10 joules is work. But I know the formula for work. Work is the integral of the force function. I also know what the force function is. So that means I know that 10 is equal to the integral of force function for springs is K times X. I also know that how much it stretched. It went from equilibrium to 0.1 meters longer because it started at 1 and now it's at 1.1. That means that X went from 0 to 0.1. Okay, I'm going to give myself a little bit of space because I think I'm going to run out of space on this page. So I'll just go from there. Let's finish calculating it. This is going to become K times X squared over 2. K was a constant. I'm doing the integral evaluated from 0 to 0.1. That means 10 is equal to K times 0.1 squared over 2 minus 0. I can multiply both sides of that equation by 2, and I got 20 equals K times 0.1 squared. And then you don't need to do this part by writing it down, but you definitely need to type it into your calculator. I just divided both sides by the 0.1 squared. Make sure you use your calculator to see what you got. I got K equals 200. Hopefully I did that correctly. Actually, let me take out my calculator and double check. I actually am not confident because I didn't type that one in earlier. So let's type that. So 21 divided by 0.1 squared. I got 2,000. I did. Sorry about that. There we go. Okay, there we go. Yeah, thank you. Good thing I typed it into my calculator. Okay. All right. So I got 2,000 there. Right. So that's what my K is, but that's not what the question said. That's just what the spring constant is. The question actually asked how much work would it take now to stretch it from its original 1 meter in length to 1.3 meters in length. So now I'm finding the work, which it was at equilibrium, and then it went 0.3 meters longer. So 1 meter was what it originally was. So that's nothing has moved. That's where the 0 came from. And then the 0.3 meters farther. And then I'm going to integrate the force function. And now my force function is K times X. And I found my K to be 2,000. So then I'm going to get 2,000 X squared divided by 2 evaluated from 0 to 0.3. So I got 2,000 times 0.3 squared divided by 2 minus 0. And I should type that into my calculator because I didn't do that earlier. So I'll do that with you guys right now. So 2,000 times 0.3 squared divided by 2. And I got 90 joules is the amount of work that would take. Ta-da! All right, let's do a little bit more. I know it's kind of tricky. That's the idea for the work with Hooke's law. Now we're going to do a little bit more. We have a lot of stuff in our section 2.5, which is now we're going to do the pumping liquid from a tank. So imagine like a tank that you have. It could be really large or really small. I don't know if that really matters. Some tank may be filled with water. Or something like that. Now you have some tank that's filled with water. What I want to do is pump the water up and out of the tank. I want to, in this particular situation, what if I wanted to take it up and out, meaning there's no way for me to drain it from the bottom. I actually have to go up and out. So I do have gravity working against me because I don't have a drain on the bottom. I'm actually pumping it out. And we're going to think about the work it takes to do that. So force is equal to, I'm going to actually rewrite this a little bit. I would say that gravity due to planet Earth, we know, but we also know that's actually acceleration. So maybe it's better to use letter A. Maybe it's not. I don't really know. It doesn't really matter. You can also say force is equal to M times A or M times G. That's fine either way. Work is equal to the force times the distance. And so I know that force is M times A. So maybe I'll highlight that for you, that this force was my M times A. That's how you should write that in your notes as well. And then here is the steps to solve these types of problems. Definitely draw a y-axis. You want to draw a y-axis. I promise you, you'll see in the example. And then you're going to try to assume that the interval corresponds to the vertical extent of the fluid. So how high do you have to lift the water out of the tank? Yeah, how high? How high do you have to lift the water to leave the top of the tank? And then you're going to look at the area of the horizontal slices and the distance each small little slice has to be lifted to leave that tank. And then the work is going to be equal to, we still have to think about the density. Remember that we're still thinking about that density. The density times the distance right there, times the acceleration times that area, and then that little dy maybe for that sliver of each one. This is something that will be given to you guys on any exam. So this is not a formula you have to have memorized. Okay, so let's do an example. That's kind of a lot of material going on right there, but let me just leave that formula up and show you an example. How much work is needed to pump all the water out of a cylindrical tank with a height of 10 meters and a radius of 5 meters? Draw a picture. These ones you have to draw a picture. I'm telling you, it's like impossible to do this without drawing a picture. Probably the ones up until now you got away without it. This one, it's not going to work. So I have a cylinder, my cylindrical tank. What do I know about that tank? I know it has a height of 10 meters and it has a base radius of 5 meters. I'm going to draw the y-axis. I don't really like negative numbers, so I make everything above. That's convenient for me. Then I have positive values instead of negative values. All right, so here it is that I have my tank that I have, that it is filled with water. So it's got all the water, it's completely filled with water, and I want to pump all the water out. I'm going to look at a little sliver. I'm going to slice this right across somewhere right here. And if I slice it right across, that'll be at a height of y, and that will change. right? It'll be from here to here to here to here. So y will change. So y should probably go from 0 to 10 from the bottom to the top. Okay, but just for that one y right there, let's take a look at the area of that cross section. So the area of that cross section, in this case, that slice was a circle. So the area of a circle is pi r squared. I'll just write r squared there. But then in this particular case, that radius we know is 5. And it's always going to be the radius is 5 for all of those slivers because it was a perfect cylinder there. So I ended up with 25 pi as the area. Then let's think about the distance that that little sliver of water has to travel. That little sliver of water right here has to be lifted out. So it's got to go out of the tank at some point right here. All right, and so what is that distance? It had to go out to a height of 10, but it was starting at a height of y. So that would be 10 minus y is the distance that that traveled. I want to point out something else. The density of water, because this particular one tells me that it's water. This is something that we should know. The density of water is constant. It's approximately 1,000 kilograms per square meter. Sorry, per cubic meter, not square. I apologize. It's an approximation, okay? But there's that 1,000. So let's do the example, or let's do the integral. Work is equal to the integral from A to B of rho times gravity times the area of each little sliver that has to travel, as well as how far each little sliver has to travel. And then I just plug and chug. So in this case, it's going to go from 0 to 10 because all of that water starts at the bottom and it's going all the way up to the top. Now, if this were a tank that was, let's say, only half filled, then this would be bounded from 0 to 5. The area, or sorry, the distance would still be 10 minus y. It still has to get out of the tank. It's just this 0 to 10 as the bounds of the integral are going to be your water. So in this case, the water was filled. Okay. So my rho, which was 1,000, my gravity, which was 9.8, my area, which was 25 pi, my distance, which was 10 minus y dy. All right, the setup is the hardest part. Now I can just plug and chug. So this is going to become, I'm going to simplify a little bit. I'm going to actually calculate it. 1,000 times 9.8 times 25 is 245,000 pi. Those were constant multiples. So I just decided to take that outside of the integral. It makes it a little bit easier for me to visualize this in a way that's not confusing. And then I do the antiderivative, evaluate from 0 to 10, plug and chug, plug in your 10. You're going to end up with 10 times 10, which is 100, minus 10 squared over 2, which is 50. So you're going to end up with 50 right there. Type that into your calculator. I got 1,225,000 pi joules. Ta-da! Okay. Let's do another one because it does get a little trickier. So now I know it's kind of a lot. You can do it though. This next one is a lot trickier. All right. So if you need to pause and rewind to rewatch that previous video, go for it. This one's a little bit trickier. All right. The next example, assume a tank in the shape of an inverted cone with a height of 12 feet and a base. Oh, and I'm sorry. Let's change all of that to meters. I apologize. Let's just do everything in meters for this problem. I don't want to convert between feet and meters. That just seems kind of annoying. So we're going to just do everything in meters. So we don't have to do that conversion. I'm never going to make you do that conversion by hand. You might have to on a homework or a project. You can use a calculator and Google for that. But on an exam, I wouldn't make you convert between feet and meters, I promise. Okay, let's draw the picture. I have an inverted cone. So think of it like an ice cream cone. So tank down here is my cone. This is what it looks like. I'm going to draw the y-axis just like we did before. Here's my y-axis. It's kind of nice to have things be positive. I do know that the height of this cone, I think it tells me was 12 meters. And then the radius, pretend I'm a good artist, it looks like was only 4 meters. The tank is full to start, so that means that my bounds on the integral are going to go all the way from 0 to 12 because it was full to start. If I wanted to pump all the water out, it would go from 0 to 12. This one's going to be a little trickier, but we can do it. So let's think about each sliver now. Now I'm going to look at one of those little slivers. I'm going to slice it right here at that height of y. Let's think about the area of that little sliver. That area is definitely pi times the radius squared. It's still a circle. The area of a circle is still pi r squared, but we have quite a big problem here. So maybe pause what you're writing and just pay close attention. This is really tricky because the radius of each one of those little slivers is different. So I can't just say the radius is 4, it's not. The radius is different. The radius for each one of those little slivers is an x value, right? Because you can see it's an x value because it's from the center to the edge and it's going in that direction. That's an x value. So we got to write that down. Okay, so now it's pi times an x value squared. So I got to find that x value, and there's an easy way to do it. I promise I got you. I'm going to take that straight line right there. I'm going to find the equation of that line. Think of it like a y equals mx plus b. And in this case, it went up 12 and over 4. And it had a y-intercept of 0. So I ended up with y equals 3x, which means x equals 1/3 y. And that tells me that my area is equal to pi times 1/3 y squared. Whoo-wee, that one got a little bit trickier. All right, we can do it. Now, the next thing I want to find is the distance that that sliver has to travel. That sliver still has to get out of the tank. So it has to get to the height of 12, so it just has to get out of the tank. It's just 12 minus y. Okay, cool. All right, and then I'm going to write down the formula. I just happen to have it memorized. I promise this formula will be given to you, but it's the integral from a to b of rho times gravity times the area of each cross section times the distance that each cross section needs to travel. And then I'm going to plug and chug. So then this is going to become my density of water is still 1,000. My gravity on planet Earth is still 9.8. The pi over 9 y squared. The distance was 12 minus y dy. We're looking good. Let's read the question again. We're missing something. Let me go back and read the question one more time. We've drawn the picture. We've set everything up. The tank is full to start, and water is pumped over the upper edge of the tank. That's out of the tank. Until the height of the water remaining in the tank is 4 meters. How much work is required? So I don't want to dump all the water out. I want to stop right here when it's at 4. That's when I want to stop. I want to stop this whole thing when it has a height. Let me get a different color so it's not confusing. I want to stop that whole thing when it has a height of 4. So it's all of this water that I need to get out. That bottom little small wedge I want to leave in, it's all of this water that I want to get out. So that's only from 4 to 12 that has to leave. So my bounds are actually only from 4 to 12. All right, then we can calculate this. We got this. So 9, let me actually multiply that out. 9800 pi divided by 9 are constant multiples. So they can come on the outside. I have a y squared, 12 minus y dy. I'll highlight that for you. It was this guy and the 9 I just took, and the pi I just took on the outside. That's all. I just simplify that. Now I'm going to distribute. If I distribute that y squared, that should be pretty easy to distribute across. That will become a 12y squared minus y cubed. Then you can integrate that. So 9800 pi divided by 9, 12y cubed over 3 minus y to the 4th over 4. Evaluated from 4 to 12. So I'm going to run out of space. So I'm going to go over here. I have 9800 pi over 9 times 4 times 12 cubed minus 12 to the 4th over 4 minus 4. The 4 came from the 12 divided by 3, by the way. 4 times 4 cubed minus 4 to the 4th over 4. And of course, probably a good idea to use your calculator here. I typed this into my calculator earlier today, so I hope I typed it in right. Double check yourself with your own calculator. Just type that in, and I got 144,907,00.83 joules. Ta-da! All right, definitely a little bit of a trickier section, so feel free to rewatch this video or maybe watch those additional videos for this one. This section 2.5 is a little bit tricky, but there we have it. I'll see you next time. Thank you.